The first example of a small system in contact with a thermal reservoir will be related to paramagnetism. We're going to consider a substance which has n zero magnetic atoms per unit volume. So this is going to be number of magnetic atoms per volume, and we're placing this substance in an external magnetic field, so we have B external magnetic field, and each atom has spin 1/2 and associated magnetic moment mu 0. Mu 0 is magnetic moment per atom, and this material is said to be paramagnetic because its magnetic properties are determined by the orientation of individual magnetic moments at a temperature T. So we have T, the absolute temperature, and what makes this material paramagnetic is that the magnetic properties are determined by individual magnetic moments. The magnetic properties determined by individual magnetic moments. So it's not a collective behavior. So the question I would like to ask is, what is the average moment of one of its atoms? So this is a key question we have. What is the mean value of the magnetic moment of one of its atoms? So we would like to answer this question. And basically we're assuming an ideal spin system here. The separation between the atoms is large enough to have weak interaction between neighboring atoms. So we have a weak, in the limit of weak interaction between atoms. So we have ideal situation, ideal spin system. So in this discussion we're going to have the small system, system A, in contact with the thermal reservoir is just one atom, because one atom does not care about the neighboring atoms. There is weak interaction, and there's going to be the heat reservoir. Heat reservoir A prime is the rest of the atoms, so it's just a thermal interaction between the rest of the atoms we have here, not a magnetic interaction, because the magnetic interaction is very weak. There are the atoms are far away. Okay, so weak interaction, this comes from a large atom to atom separation, and therefore the only interaction I have between these atoms is a thermal interaction. So system A can be in one of two states. It can have a sigma positive state, which means it has a plus mu 0 magnetic moment. The corresponding energy to this state will be epsilon plus, is minus mu 0 b if the magnetic field is pointing up. So it is the minus the dot product. So let me remind you, energy is minus the dot product mu with b. So it's minus mu 0 b if they are parallel. The system A can be in the minus state with a magnetic moment minus mu 0. The moment is pointing down. Then the energy will be higher, plus mu 0 b. And the probability of having a plus state, so the corresponding probability of having a plus state will be given by the canonical distribution, the constant c times e to the minus beta epsilon plus. So this is going to be c times e to the beta mu 0 b, and the corresponding probability for the negative state, minus state, will be c times e to the minus beta epsilon minus, which is c times e to the minus beta mu 0 b. So you can see that the plus state is favored in this situation. And furthermore, I need to have the normalization of these probabilities. So p plus p minus, this has to be equal to c times e to the beta mu 0 b plus e to the minus beta mu 0 b equal to 1. So I can find this constant c as well. And here you can see how these probabilities vary with mu 0 b over kt, which is beta mu 0 b, right? So let me remind you that beta is 1 over kt. So I'm going to call for the rest of this discussion beta mu 0 b over kt. I'm going to define this to be omega, and we can see that the probability varies as a function of omega. So if you have, for example, a large magnetic field, the probability of having, at constant temperature, probability of having a plus state increases. You can see here, if you have a large magnetic field, the probability of minus state, anti-parallel moment, decreases, as you can see here. On the other hand, for a constant magnetic field, if I increase the temperature, this is going to decrease omega, and the probabilities will approach each other. So you can see that they will be in the limit of infinite temperature, omega equals 0, the probabilities will be the same. On the other hand, if I have a very low temperature, omega is large, the probability of the plus state will be much greater than probability of the minus state. So basically I have defined this quantity omega, which is beta times mu 0 b, which is mu 0 b over kt. And by the way, I should finish this calculation here. This constant c in the probability distribution I found from the normalization condition to be 1 over e to the beta mu 0 b plus e to the minus beta mu 0 b. Okay, so let me check what I have seen in this plot mathematically. If temperature is very large at constant magnetic field, what happens to omega? Okay, so constant magnetic field, omega goes to 0. So in the limit, omega is much less than 1. What happens to these probabilities p plus and p minus? The probabilities basically approach each other. So we see that P plus approaches P minus. So they're going to be equal probabilities eventually. And the other thing I want to check is what happens if the temperature is very small. If temperature is very small at constant magnetic field, in this case, the probability of the minus state, let's look at the probability of the minus state. It's here. As omega goes to infinity, the probability of the minus state goes to 0. So this is going to go to 0. Probability of the plus state will go to 1. And we will have a mean moment of mu 0. It's going to be pointing up. On the other hand, for the previous scenario, the mean moment should be 0 because we have equal probabilities for this limit, high temperature limit. So in general, what is the average moment of one of its atoms? This was the question of interest. The average moment is by definition, using statistical definition, probability of the plus state corresponding to the positive moment mu 0, probability of the minus state corresponding moment minus mu 0. So this is going to be mu 0 times the probability of the plus state is c times e to the beta mu 0 b. So it is mu 0 times, I'm going to have a ratio here, e to the beta mu 0 b, and then I will have, because of the minus mu 0, minus sign, e to the minus beta mu 0 b, and then because I have this c here, I'm going to use the result from that. So multiplied by c gives me e to the beta mu 0 b plus e to the minus beta mu 0 b. Now, basically, I would like to find out if there is a better way of describing this mu bar. So if you remember from hyperbolic functions, cosine hyperbolic a is e to the a plus e to the minus a divided by 2. Sine hyperbolic function, sine hyperbolic a, is e to the a minus e to the minus a divided by 2. So tangent hyperbolic a will be e to the a minus e to the minus a divided by e to the a plus e to the minus a. Therefore, with this, I basically see that the mean magnetic moment per atom will be mu 0 times tangent hyperbolic omega, where omega is beta mu 0 b. So this is going to be the answer to the question that I asked initially, the average moment per atom. Now, at this point, we can talk about the total magnetic moment per unit volume, the mean value. So we define the magnetization M. Let's consider its mean value. It's going to be the mean magnetic moment per unit volume. So this is going to be, let's call this M0 bar. M0 bar will be the sum over all moments average value divided by the volume V. Well, since I have ideal spin system, these moments do not interact with each other. Basically, this is going to be the sum over all average moments per atom divided by V, it will simply be n times mu I bar divided by V, which is n0, number of atoms per unit volume, number of magnetic atoms per unit volume, multiplied by mu I bar, where mu I bar for the ith atom will be equal to the mu bar that I calculated, mean value of magnetic moment per atom. So I find that the magnetization mean value, mean magnetic moment per unit volume, will be number of magnetic atoms per volume multiplied by the average moment per atom. So it's going to be n0 times mu bar. Now I want to see what happens to the behavior of the tangent hyperbolic function in the limits that I have considered. So if you look at the limit omega much less than 1, this would be the high temperature limit or low magnetic field limit. Okay, so high temperature, low magnetic field. So omega is going to be very small. This will be giving me, for the exponential function e to the omega around omega equals to 0, Taylor series expansion, e to 0 plus the derivative of e to the omega evaluated at omega equals to 0 multiplied by omega minus 0 and higher order terms. So this will be 1 plus omega. And in the other exponential, e to the minus w, for w is equal to 0, I have e to the 0 plus dd omega e to the minus omega evaluated at omega equals 0, omega minus 0 plus plus. This will be 1 minus omega. So if I look at the behavior of the tangent hyperbolic function, tangent hyperbolic omega, which is e to the omega minus e to the minus omega divided by e to the omega plus e to the minus omega, will become 1 plus omega minus 1 minus omega divided by 1 plus omega plus 1 minus omega. You can see that these omegas will cancel, and at the end I have here 2 omega divided by 2, which is omega. So it's going to behave like omega. In the other limit, so this is the first case that I considered. In the second case that I will consider, if omega is much greater than 1, you will have e to the omega will be dominating over e to the minus omega, and tangent hyperbolic omega will become e to the omega over e to the omega, which is 1. Okay, so for the mean moment value, so for the first case, omega much less than 1 case, this is the first case, I have mu 0b over kt much less than 1, or mu 0b much less than kt, again high temperature, low magnetic field limit. In this case, my average magnetic moment, which was mu 0 times tangent hyperbolic omega, has now become mu 0 times omega, because tangent hyperbolic omega is omega in this limit. So this will be mu 0 square b divided by kt. For omega much greater than 1, for omega much greater than 1, the second limit, where I have mu 0b over kt much greater than 1, or mu 0b is much greater than kt. This is the low temperature, high magnetic field limit. So there I will have mu bar is equal to mu 0 times tangent hyperbolic omega. Tangent hyperbolic omega is 1, so mu 0 times 1, it is mu 0. You can see that indeed as t goes to infinity for the first one, mu bar will go to 0. So in the previous discussion we had here, we have found that the probabilities suggest if the temperature is very large, the probability of plus and minus states should be equal. Mu bar should go to 0. If the temperature is very small, we have the probabilities approaching each other. Mu bar should be mu 0. So that's basically recovered in this mathematical treatment. So in the first case, for mu 0b much less than kt, the first case, if I look at the average magnetic moment per unit volume, that is magnetization, it is n0 times mu bar, and that is going to be n0, number of magnetic atoms per unit volume, mu 0 square b divided by kt. Now this can be written in the form chi times magnetic field B, where chi is defined as the ratio of the mean magnetic moment per unit volume, magnetization, divided by the magnetic field. This is called magnetic susceptibility. Magnetic susceptibility. Okay, so since I have no interaction between atoms in this limit, the magnetic field that I see from outside is the B field. This is a technical detail, but B is the magnetic field inside the material, H is the applied field, but these two are the same in this limit because I have a small number of non-interacting spins. So therefore, to a good approximation, B and H are the same. And using this definition of magnetic susceptibility, because normally magnetic susceptibility is magnetization per H field, not B field, but here they're almost the same. So I find that the susceptibility should be n0 mu 0 square divided by kt. So the susceptibility of a paramagnet is number of magnetic atoms per unit volume multiplied by magnetic moment per atom square divided by kt. The fact that the susceptibility varies with 1 over T for a paramagnet is Curie's law. Okay. Now, if you look at the behavior for a large omega value, high magnetic field value, the second case, so this was the first case I looked at. In the second case, I will have a large magnetic field when mu 0b is much greater than kt and or low temperature. The total magnetization, the magnetic moment per unit volume, will become n0 times mu 0. And this value in this limit is called saturation magnetization because it saturates at this value. So you can see here, if I plot The magnetization divided by n0 mu 0 as a function of omega, so this is my omega here, I can see that for low values of omega, I have a linear dependence on magnetic field, and actually, if you consider the slope of this curve, the slope is magnetic susceptibility chi. Now this slope is going to be decrease and decrease when we go to large omega values, and eventually it will saturate, and this high value of omega where it saturates, we're going to see saturation. So when it becomes 1, m0 bar is n0 mu 0, that is saturation magnetization. And for low values of the magnetic field, we have a linear dependence on magnetic field. And also, the way the slope varies with temperature is 1 over T behavior. It's called Curie's law. So let's summarize what we said about paramagnetism. Remember, we're talking about a small system in contact with a thermal reservoir which obeys the canonical distribution. If you have n sub 0 number of magnetic moments per volume with magnetic moment per atom mu 0, B is external magnetic field, T is absolute temperature, and we are neglecting interactions between moments. So the only interaction between moments is thermal interaction. So the small system A consists of one atom, one moment, heat reservoir is rest of the atoms with which we have a thermal interaction, and we're considering what is mu bar of one of the atoms, and well, you can say that heat reservoir is also the rest of the atoms plus the ambient, the environment, because everything is in thermal contact. So if you consider for a single atom, it can have a plus mu 0 or minus mu 0 magnetic moment with corresponding energies minus mu 0 B and plus mu 0 B, because the energy of a magnetic moment in a magnetic field B is minus mu dot product with B. The probability of having a positive moment is C times e to the minus beta energy of that state, which is minus mu 0 B, so it becomes C times e to the plus beta mu 0 B, and for the other case we have e to the minus beta mu 0 B. The probabilities should add up to 1 as usual. We have normalization, so the constant C we're talking about is 1 over e to the beta mu 0 B plus e to the minus beta mu 0 B. Beta mu 0 B appears everywhere, so I define it as omega, which is mu 0 B over kT. In the high temperature limit for constant magnetic field, for example, omega is approaching 0 or omega is much less than 1. What happens to these probabilities? When omega approaches 0, we are approaching C times e to the 0 for both cases, so they're going to be equal probabilities, which means the mean moment per atom should be approaching 0. If the temperature is small for constant magnetic field, the probabilities, so this is going to correspond to omega much greater than 1 limit, and in this case you will have e to the plus beta mu 0 B dominating over e to the minus beta mu 0 B. So you will have P plus increasing and P minus decreasing. P plus will go to 1, P minus will go to 0. The plus state has magnetic moment mu 0, so the mean moment should be approaching mu 0. What is the mean moment in general for any given temperature or magnetic field? It's by definition probability of the state multiplied by the corresponding value added over all possible states. We have two possible states, plus and minus, P plus times mu 0 plus P minus times minus mu 0. And using hyperbolic functions, I realized that the answer that I'm getting is mu 0 tangent hyperbolic omega. And the magnetization is mean magnetic moment per unit volume. It's just number of atoms per volume multiplied by the mean moment per atom. And this is due to the fact that the mean moment per atom does not change from atom to atom because the atoms do not interact. It's the same value, so I just add them up I go from I equals 1 to n here, the total number of atoms, and I find that n divided by v is number of atoms per volume, and 0 times mu bar is m bar. So if I look at my limits again, omega much less than 1, high temperature, low magnetic field limit, Taylor series expansion tells me exponential becomes 1 plus omega for e to the omega and 1 minus omega for e to the minus omega. By substituting these two limits, as omega goes to infinity, omega is much greater than 1, it should behave as omega. Tangent hyperbolic omega is replaced by omega. So for omega much less than 1, that is this limit here, you can see that it's going to be varying linearly with omega. So it has a tangent hyperbolic omega becomes omega. And if omega is much greater than 1, low temperature, high magnetic field limit, tangent hyperbolic omega becomes 1. So in these two limits, I find that mu bar should be, for the case omega much less than 1, mu 0 omega, mu 0 square b over kt, and in the other limit, omega much greater than 1, low temperature, high magnetic field, mu bar becomes mu 0. So if you look at the corresponding magnetization value, it becomes n0 mu bar for the first limit, omega much less than 1, high temperature, low magnetic field limit. We see a linear dependence on magnetic field. The coefficient is chi, magnetic susceptibility, the ratio of the magnetization to external magnetic field. An external magnetic field, I don't call H here, I call it B, because H and B are almost the same, because I have non-interacting spins. And so this magnetic susceptibility is n0 mu 0 squared divided by kt. It's proportional to 1 over t, that's Curie's law. In the other limit, when mu 0b is much greater than kt, m0 bar becomes n0 mu 0, that's saturation magnetization. And you can see in this plot here, we have a saturation region for omega much greater than 1. So this is omega much greater than 1 region, and this is omega much less than 1 region, where I have a linear dependence. So this basically summarizes what is happening in paramagnets, and we were able to derive Curie's law using canonical distribution for the